Alrighty, welcome to second lecture for this week. Oh, just realized my video's not on. There we go. All right, so today I guess we'll practice some more with triple integrals, get that going. So if you remember yesterday, we talked about with triple integrals, the main first step to getting going is setting up the innermost bounds. And so the ones we looked at yesterday, we put dz on the inside. Oh shoot, I just realized I'm not in the right program here. All right, so yeah, like I was saying, for this, let's start off by putting dz on the inside. And so what do you do with the z bounds? The z bounds correspond to the bottom and top surfaces. So the bottom surface is your lower bound, and then the top surface is your upper bound. So this is kind of like the picture we had for double integrals, just a little bit more involved since we're dealing with a solid region as opposed to something in the xy plane. But yeah, that's the idea, is you have your z equals u1 of xy is your bottom surface, z equals u2 of xy is your top surface, and for that bound your solid region E. Okay, and then the next step is to then figure out this shadow D in the xy plane, and basically for that you do exactly whatever you would have done for a double integral over that region. Okay, so let's just do another practice one. Let's set up the triple integral of f of xyz dv, where e is above z equals 4, below z equals 10 minus x squared minus y squared, and inside the parabolic cylinders y equals x squared and x equals y squared. So anyway, I don't think I'm going to be able to do a very good job of drawing this, but what I start to think of here is, well, we have our plane z equals 4, which is going to look something like that. And then our equation z equals 10 minus x squared minus y squared, that's a parabolic, or I'm sorry, an elliptic paraboloid opening down from z equals 10. So that's our z equals 10 minus x squared minus y squared. And then we have these parabolic cylinders, x equals y squared and y equals x squared. Essentially, those parabolic cylinders are going to tell us what's going on as far as the x and y values go for this solid region. So like I said, I'm a little bit scared to draw this, but if we think about what's going on in this xy plane shadow, you know, y equals x squared is this parabola, x equals y squared is that parabola. And so essentially you want to think about these parabolic cylinders as sort of all the cross sections perpendicular to the z-axis are the same parabolas. So you have these parabolic cylinders that kind of go up like that. And so essentially that's just telling us our shadow D. That, oh God, I might be able to draw this. Let's see here. Such that overall I have this piece that lives in z equals 4, and then I have this piece that kind of looks like that. So it's only the stuff between the plane and the elliptic paraboloid that's above that little, I don't know, leaf-shaped region. So this orange region in the xy plane, that's the shadow D, and our solid region is that blue solid region that I drew there. Okay, and so anyway, thinking about it, it looks like we can do our z on the inside, and our bottom surface is the plane z equals 4, and our top surface is the elliptic paraboloid z equals 10 minus x squared minus y squared. So that goes on your upper bound. Okay, and then as far as our x and y bounds go, they're going to be whatever we would have done for the double integral bounds of that shadow d. So we could do it dy dx. It looks like y equals x squared is the bottom curve. X equals y squared is the top curve, but we have to put it in the form y in terms of x. So our top curve is y equals square root of x, right? So I guess y is plus minus square root of x on that sideways parabola, but the top half is when we take the positive square root. And so that's our upper limit for x. And then finally, this intersection occurs at 1, 1. So our x bounds are going to be 0 to 1. So when you're reading this setup, if you see the two surfaces of the form z in terms of x and y, that's probably going to be your innermost z bounds, your bottom and top surfaces. And then the other two things, the parabolic cylinders, that I guess I can try and, I'm not going to try to draw it on the same picture, but the parabolic cylinders are going to look something kind of like that, sort of like a trough that's sitting vertically like that. And then I guess the other one looks like that. So the parts that they have in common are sort of that leaf-shaped region that we saw. So anyway, that's how you could set that up. What do we got next? So this one I'm actually going to go through and calculate. And so just as a refresher, think of 2y as the density of a solid object. And therefore, this triple integral is calculating mass. So remember, you only think of volume when you're doing the boring constant integrand 1. So the triple integral of 1 is the volume. Otherwise, you want to think of triple integrals as the mass of a solid object. And your integrand is the density function. Okay, so anyway, same kind of thing. Calculate this where E is above the plane z equals 3 plus x minus y, below the plane z equals 10 plus x plus 2y, and inside the cylinder. So I don't know how these planes look. It's not so important. But let's say that z equals 3 plus x minus y looks something like that, and then z equals 10 plus x plus 2y looks something like that. So it's in between these two planes and inside a cylinder. So I guess our solid region E would look something kind of like this, where our bottom surface is the one plane and the top surface is the other plane. And so our innermost z bounds are going to be 3 plus x minus y up to 10 plus x plus 2y. And then what I'm going to show you, the reason I picked this example is that if you want to, you can fully set up the xyz triple integrals. So for example, you could do, x goes, be careful, this is a disk, right? The fact that we're inside the cylinder tells us that the shadow in the xy plane is this unit disk. And so if you wanted to do xyz bounds for that, you'd have to do it as follows. Minus 1 to 1, minus square root of 1 minus x squared to plus square root of 1 minus x squared, and then 3 plus x minus y up to 10 plus x plus 2y. So that's the way you would fully set it up. But I think it's actually easier to just leave it like I did here. So technically that's not a full, what I just boxed isn't a fully set up triple integral because I haven't made explicit the x and y bounds, but I've indicated that the x and y bounds are for the disk of radius 1. And so it actually kind of makes a little sense to just leave it like that. Let's do that first step. So let's do the inner z anti-differentiation, right? So what's the first step? You do antiderivative of 2y with respect to z, so you of course get 2yz, and then you plug in z equals 10 plus x plus 2y, and z equals 3 plus x minus y. And when you do all this out, I'm going to get the double integral on the disk of, well, it's going to be 20y plus 2xy plus 4y squared, yeah, plus 4y squared. And then minus, it's going to be 6y minus 2xy, and then plus 2y squared. So as I guess you kind of could have seen that the x's were going to cancel when you plugged in and subtracted. So anyway, it looks like we're going to get the double integral of 14y plus 6y squared. And so now at this step, we could do a little trick that I showed you yesterday, that this disk, x squared plus y squared less than or equal to 1, I'll use blue for this, well, I'll use red, is symmetric over the x-axis. And the term 14y is odd with respect to y. So the entire integrand isn't odd with respect to y, but 14y is. So I guess technically what I'm going to do is recall that I could split up the double integral into these two pieces, and then this integrates to 0 because 14y is odd with respect to y, which means that whatever this point is contributing is canceled out by this point, right? Because they have opposite y values. And so anyway, that cuts down on a little bit of work. And then at this stage, the reason why I didn't want to write out all this stuff is that I kind of knew as soon as I saw that disk shadow that I was eventually going to use polar coordinates. So how is that going to work? Well, r goes from 0 to 1, theta goes from 0 to 2 pi, 6r squared sine squared theta, r d theta dr. Don't forget your extra r that comes in from your dA. And then at this stage, we can, I don't know, I guess do our theta integration. So 0 to 1, 6r cubed. So the trig identity that we're going to have to use is, this isn't an antiderivative yet, but the identity for sine squared theta is 1/2 minus 1/2 cosine of 2 theta. And I guess, yeah, sorry, I didn't take the antiderivative yet, so this is still 0 to 2 pi, 0 to 1. And so then my theta integration is 0 to 1. So 6r cubed, and then this ends up being pi, because sine of 4 pi, sine of 2 pi are all, sorry, yeah, sine of 4 pi and sine of, oh God, I'm getting ahead of myself. So anyway, yeah, the theta antiderivative is theta over 2 minus sine of 2 theta over 4. And when I plug in 0 and 2 pi, I'm just going to get left with pi. So 0 to 1, 6r cubed pi dr. Because, as I was saying, sine of 4 pi and sine of 0 are both 0. So anyway, you get this, and so whatever this is, 3/2 r to the 4th pi 0 to 1. So what, 3/2 pi is our answer. So anyway, a lot of that, not so bad. Just make sure you remember the identity for sine squared theta so you're able to anti-differentiate. And like I said, you could write this out as a fully set up triple integral with all of your x, y, and z bounds, but because of that disk, you're going to want to switch to polar anyway, so you might as well just kind of leave it like I did right here. And so next week, we'll learn something called cylindrical coordinates, which will allow us to make that transformation to r and theta when we're still on the triple integral. But there's no reason why we can't do the first step of this triple integral, and then once I'm left with the double integral, do the conversion to r and theta at that stage. And so again, if you hadn't noticed this symmetry, then you would have had that go away when you do the theta antiderivative, because your y would have a sine theta, which antiderivative is basically minus cosine theta, and when you plug in and subtract, cosine theta is 2 pi periodic. So anyway, that would go away even if you didn't see that symmetry trick. All right, so then I guess what else can we do for today? We could start to be a little bit flexible with regards to which variable goes on the inside. So the examples we've looked at so far, we've had dz on the inside. And sometimes you might want to take that picture and rotate it around a little bit and maybe have x on the inside. So for example, let's set up, think about setting up with dx on the inside. And so essentially it's the same picture, just rotated. So in this case, you're going to have your bounding surfaces given in the form x in terms of y and z. So before, when we had z on the inside, you wanted to think about your top and bottom surfaces. So your points in your solid region start on the bottom surface, you go straight up to the top surface. So going straight up is parallel to the z-axis, right? You're letting z start there and stop there. If you're keeping x and y the same, you're just letting z start there and stop there. So the analogous idea with x on the inside is that you have these, you're going parallel to the x-axis. So you're starting on this surface, x equals u1 of yz, and you're going parallel to you're increasing x, you're keeping y and z the same, and you're stopping at x equals u2 of yz. And so then that's your first step, remember the inside bounds. And then your bounds for y and z are just going to be the shadow d in the yz plane. So it's going to be the same idea where you have your double integral type bounds for the outer two variables, except the shadow you're doing is now into the yz plane. So as an example, let's set up this triple integral where dx is on the inside, and our solid region is the solid tetrahedron with vertices 2, 0, 0. So let's let this be my x-axis. So 2, 0, 0, 0, 0, 0, so the origin, 0, 1, 0, and 0, 0, 1. So this is my z. And so tetrahedron, remember, is just 4 triangular faces. So you have the xz triangle, xz plane triangle. You have a triangle in the yz plane. You have a triangle in the xy plane. And then you have this diagonal triangle through the points 0, 1, 0, sorry, 0, 1, 0, 0, 0, 1, and 2, 0, 0. Okay, so that's our solid tetrahedron. And if we're asked to put dx on the inside, then we're thinking in this perspective of our back and front bounding surfaces. So if you think about it, the back surface is the yz plane, which is given by x equals 0, of course. And then the front surface is the plane through the points 2, 0, 0, 0, 1, 0, and 0, 0, 1. And so yesterday I showed you, I refreshed your memory of how if you know a plane equation, you can pretty quickly get the x, y, and z intercepts. Well, what we're going to do is run that in reverse. So we're going to start with these intercepts and come up with the plane equation. So you could get the displacement vectors between two of the points, get two of those displacement vectors, take the cross, do the plane equation, you can do that. But the shortcut here would be to do x over 2 plus y plus z equals 1. So a plane with, I think the formula I gave yesterday was a 0, 0, 0, b 0, 0, 0, c is x over a plus y over b plus z over c equals 1. So certainly that is a plane equation. It contains the 3 points that we want, and therefore, because a plane is defined by 3 points, that has to be the plane that we're after. And so anyway, this front surface, I have to get it into the form x in terms of y and z. So I just do whatever I have to do for that, which is going to be x is 2 minus 2y minus 2z. So solve for x. That's our front surface. And therefore, our innermost x bounds are 0 to 2 minus 2y minus 2z. And then our y and z bounds are just going to be the shadow in the yz plane, which, be careful, it's not a rectangle, it's a triangle. So this, it's going to be a little bit hard to draw, but yeah, of course, the shadow here is that triangle in the YZ plane. And so now it's just the same story of bottom curve to top curve, so 0 to 1 minus y for z. And so yeah, this would be then 0, 1, 0 to 1 minus y, 0 to 2 minus 2y minus 2z, f of x, y, z, dx, dz, dy. You could, of course, done dx, dy, dz if you had set up the outer bounds as dy, dz, but might as well go dz, dy. All right. So this tetrahedron, we could have just as easily done with dz on the inside or dy on the inside, but this was good practice just putting dx on the inside. So what do we got next? Okay, and so again, what's so special about dz inside or dx inside? Nothing. Sometimes you might want to put y on the inside. So it's the same exact picture. You have your, I guess, your left surface and your right surface given in terms of y in terms of x and z. And then you have your shadow into the xz plane for your double integral bounds for d. All right, so calculate the volume of the solid bounded by the elliptic paraboloid y equals 9 minus x squared minus z squared and the xz plane. So let's see here. I guess I can make this my y-axis. And so I have this elliptic paraboloid opening to the left from y equals 9. Okay, so to find the volume, remember this is the special case for a triple integral, that the volume is just the triple integral of dv. So we take our density function to just be 1, the boring constant function 1, and therefore, yeah, when your density is a constant 1, the mass and the volume are the same, right? 5 grams of water take up 5 cubic centimeters of space. Water is special, it's got density 1 in appropriate units. Okay, and so yeah, I think with this, it's up to you. You could, if you put dz on the inside, you could do bottom to top surfaces. But I think it's best to do dy on the inside because you're already given the surfaces on the left and the right from this perspective, y in terms of x and z. So it looks like y equals 0 is the left surface, and y equals 9 minus x squared minus z squared is the right surface. And then we could do the same kind of thing as we did a couple examples ago, where we leave the outer bounds just as the disk x squared plus z squared less than or equal to 9. We don't have to write out the x and z bounds because we're probably going to switch to polar coordinates to deal with that. So yeah, do the innermost dy integration. Well, antiderivative of 1 is y, and so therefore I get double integral over the disk of 9 minus x squared minus z squared. And so then I can convert that to polar. So 0 to 3, 0 to 2 pi, 9 minus r squared, r d theta dr. Again, don't forget your extra r from the dA. And then from there, it's not too exciting. You guys can practice that on your own. Not so bad. But yeah. You could have also done, for example, just for fun, that z, if you solve for z on the top half of that elliptic paraboloid, you get that z is plus the square root of 9 minus x squared minus y. And down here, you'd have z is minus the square root of 9 minus y minus x squared. And those would be your bottom and top surfaces. And then your shadow in the xy plane wouldn't be a disk anymore. In the xy plane, it would look like this parabola type region. So, okay, let's draw that. Your y would stop at y equals 9 minus x squared. So we're at the fattest part here, which is in the xy plane where z is 0. So the part of that, the trace of that elliptic paraboloid in the xy plane is the parabola, y equals 9 minus x squared. And so yeah, y would start at 0, stop there, and then x goes minus 3 to 3, and then dz dy dx. So that's perfectly fine too. I don't think it's as easy to do. How does that end up working out? So the z antiderivative is no big deal. The y antiderivative, you get some stuff to the 3 halves. I think you're going to need a trig substitution in order to take care of that. But can if you want. But I think that's the other way. I'd say that this is the best way. Because instead of messing around with this elliptic paraboloid equation, solving for z, you just leave it y in terms of x and z and use your y bounds on the inside. So no reason to make your life more complicated and set it up with dz on the inside, but it is up to you. Okay, and then so I guess a lot of this stuff you're just going to have to practice. We picked a lot of the homework problems to give you a broad list of examples to hopefully get you to get the hang of it. With these triple integrals in the solid regions, it could be very, very difficult to visualize and very, very difficult to get set up. So remember when we talked about double integrals, we had that idea of type 1 versus type 2 regions, and sometimes you had to split regions up and it could be kind of a pain. you could have even worse things happen now that we're in 3 dimensions. So I briefly mentioned yesterday that I guess there are 6 orders that we can do. And so sometimes you might have to split things up, and not everything can be done in a particular order in one piece. But yeah, the examples we'll have you do aren't going to be too terribly difficult to visualize. But anyway, I figured I could give you a hint on, I think, the last homework problem from this week, which was rewriting a triple integral in the other 5 orders. And so it turns out that I think I can't remember if this is the question on your homework or not, or if this is just a similar one from the book. But anyway, let me give you some tips for how to do this. So it turns out there's basically 3 levels of difficulty for getting these other 5 orders. That some of the orders are going to be really easy to get, some of them are going to be sort of medium difficulty, and then finally the last type is going to be hard. And as far as the first 2, the easy and the medium, that's stuff that we've been doing since last week with double integrals. So for example, when you're looking at something like this, if you can sort of switch the bounds in the naive way, so in the way that works for rectangles in double integrals. So for example, 2 to 3, 0 to 5, dy dx, because those are numbers, you can do 0 to 5, 2 to 3, just make sure that you keep the x values with dx and the y values with dy. So that's what I'm sort of meaning to do by my figures like that you flip both together to get the new thing. So if it turns out that you get a permissible configuration, then you are allowed to just do that. So by permissible, I mean, it makes sense and gives a number as the answer. So that's our number 1 rule for these multiple integrals, is that in order to make sense at the most basic level, when you do the iterated integral procedure, it should spit out a number. So when the bounds are all numbers, that works. If the bounds aren't all numbers, then you end up getting nonsense when you try that. So 2 to 3, 0 to x, if you do that same naive switching, you get an x on the outside, which is not allowed, right? Because the last step would be plugging in 0 and x and subtracting. Your last step for this would be plugging in 0 and 5 and subtracting, and that's fine. Okay, so when you're looking at something like this, well, I guess I can review that for triple integrals. So just to refresh your memory on where variables are allowed to be for triple integrals, your outer bounds have to be numbers. Your inner bounds can have the outer variables. So that's the rule for double integrals. For triple, the outer has to be number, the middle can have the outer, and the inner can have the other 2. So anyway, when we're looking at something like this, if we could do a naive switch and it follows those rules, then that's okay. So I'm not going to show you all 5 orders. I'm going to show you, I guess, 3 of them right now. So what's one of the easy steps? So if I start with what's given, dy, dz, dx, and I switch the y and the z to give me dz, dy, dx, I claim that that's okay, because I try that and I get f d z dy dx. So yeah, all I did was switch the y and the z, and this is okay. Since, remember, your z bounds can have x's or y's, your y bounds can have x's, and then your outermost bounds have to be numbers, and this certainly follows those rules. So you could try and draw this. What does this end up looking like? Well, it's like a parabolic cylinder cut off by a plane. It's a little bit tricky to visualize, but with these, you don't actually have to draw the 3D picture. So for this homework question, you can take care of all of it either by doing this naive switching or drawing a 2D picture. So you still have to draw for some of them, you just don't have to draw 3D. Okay, so yeah, if you can do a naive switch and get something that follows the rules, then that's the correct thing to do. So just switch dz and dy and their appropriate bounds and you're fine. Okay, so that's the dz, dy, dx ordering. Let me show you the medium level difficulty. So the medium, so what happened for easy was that we left the outermost alone, we switched the inner, and that's fine. So the medium difficulty is going to be taking what we start with, dy, dz, dx, and switching it to dy, dx, dz. So you leave y alone on the inside. Okay. So what's that going to end up being? Well, it's going to be basically what we did for double integral switching. So I'm not going to pay attention to the y stuff at all. I'm just going to focus on the x and the z stuff. So it sounds like x is going from 0 to 1, and z is going from 0 to 1 minus x squared. And so that is a parabola type shape that looks like that. So z equals 0 is the bottom, z equals 1 minus x squared is the top. So that's my dz dx picture of it. Just so things don't get too busy, I will draw a new picture for dx dz. So dx dz, I have to do my left and right curves. And it looks like x starts at 0 and stops at square root of 1 minus z. So I had to solve for x in terms of z. And there we go. This also occurs from z 0 to 1. So 0 to 1, 0 to square root 1 minus z, 0 to 1 minus x. Yeah, so I left y alone on the inside. I'm just messing around with dz dx going to dx dz. And as you could see, I didn't do anything with the y. I just did this like we did double integrals all the way back to last week. And so finally, what is then the new type of thing you have to do for this problem? The new type of thing would be going from dy dx dz to dx dy dz. And so it's hard because if you do the naive switch, you get something that doesn't make sense. This is bad. Make this red. It's bad because the middle variable, or sorry, the middle bound can't have inner variable. You're only allowed in your bounds to have stuff that appears outside. So if you scroll back up, middle bounds can contain the outer variable, not the inner variable. So x is inside of where it's appearing here. That's no good. So we can't just do the naive switch. We actually have to draw the picture and do it like a double integral. It just gets a little bit trickier because we have this this square root of 1 minus z. So when we go to draw what's going on here in the xy plane, it's saying that x is going from 0 to the square root of 1 minus z, and y is going from 0 to 1 minus x. So y equals 1 minus x, that's my top curve. But I'm not going all the way from x goes to 0 to 1. So this is the one time where we kind of look at the z bounds on the outside. So when you look at this here, z is between 0 and 1, which means that if z is between 0 and 1, so is the square root of 1 minus z. So basically what happens here is that you're going to have to draw in this square root of 1 minus z as it's going to result in this xy picture being a trapezoid as opposed to that entire triangle. And then this is kind of a mess because, yeah, this is the dy dx picture. To switch it to dx dy, it's not type 2 because it looks like the right curve changes. That sometimes well, it looks like no matter what, x starts at 0, but then for part of it, it stops at x equals 1 minus y. And then at other parts of it, it stops at the vertical line, x equals square root 1 minus z. So good God, we got to split this all up. So for z between 0 and 1, and then this point here is going to be square root of 1 minus z, comma 1 minus square root 1 minus z, because y is 1 minus x, or vice versa. And I think my iPad is freezing. There we go. Oh, or I think this new version of Notability draws in shapes sometimes when you don't want to. Whatever. So anyway, yeah, we were on the curve y equals 1 minus x. So this point here is square root of 1 minus z, comma 1 minus square root 1 minus z. And so yeah, for y from 0 up to 1 minus square root 1 minus z, x starts at 0, it stops at square root 1 minus z. And then for y between 1 minus square root 1 minus z and 1, x starts at 0 and stops at 1 minus y. And so that's pretty tricky. I would say practice the rest of the homework, review double integrals before really trying to wrap your head around this. This is a lot trickier than what we were looking at before. So go ahead, slow that down, rewind it. But essentially this square root 1 minus z, think of z as just being a number between 0 and 1. So this is 0 to like 0.5, 0 to 1 minus x. When you go and draw that, you get a trapezoid, not a triangle. And so that's why you have this changing of the right curve, which requires you to split it up. So anyway, that's just a taste for how tricky some things can be. But I think it is good practice to work with all the orders. You get a feel for what's correct, what's plausible, what's not. You get some extra review of double integral bound switching, as well as some trickier double integral bound switching. But anyway, that's about all I had in mind for today. I guess I will see you next week. So again, remember 2:30 people, you do have your midterm 2 opening on Saturday, July 6th. So make sure you have that scheduled in Examity. 232 people, you got another week before you got an exam to worry about. So anyway, I will catch you later and have a good week.